Welcome to Unit 4, Force and Motion, Lesson 3, Motion Mastery Session with Mrs. Burt. So Lesson 3, Motion, is all about the relationship between the motion of, an object, a car, or a person, and speed and distance, and how those three things relate to each other. So motion can be described in three different ways: translational, rotational, and vibrational. When we're talking about vibrational motion, that refers to a rapid back and forth movement of the kind often found in particles. A rotational motion is when objects spin in place. For example, a ballerina. So a ballerina does not move, she could spin, and move left or right or up and down. But let's say, for example, a ballerina is spinning in place, not moving left or right or up or down. That would be an example of a rotational motion. So just a spin. A translational motion is a type of motion in an object that results in a change of position from point A to point B. So the other two types of motions are different from that translational motion. So when we're talking about the translational motion of an object, we're talking about a type of motion that results in a change of position from point A to point B. An example of translational motion would be, for example, a leaf blowing in the breeze. If that leaf, rolled down the road or across a lawn or across a field, it is moving from its starting point to another spot. So that would be a translational motion. Let's add in position. So let's discuss movement in relation to the position of an object. One way that we can show movement and position is by using a coordinate system. And a coordinate system is a set of lines, a set of points, lines, or directions that can be used to describe the position of objects. A reference point is an object or position about which motion is defined. So a coordinate system is an exact set of points in lines and directions, whereas a reference point doesn't always have to be exact. For example, if you were flying a kite and you said, "My kite got as high as that tall oak," that's not an exact point. You're not saying it got 23 feet in the air. It's more of a reference. Distance is described as how far an object travels. So distance does not relate to direction. It's just how far an object traveled. Displacement, on the other hand, is the distance and the direction from a reference point of an object that has undergone motion. So with displacement, you have to add in that direction. And there is a difference between distance and displacement that we are going to look into a little bit deeper. So I have this square. Let's, for example, say that this is a square block in a town that either you live in or that is next to where you live. And we want to find what is the distance traveled and what is the displacement. So if you live in house A and your friend lives in house D, and you're going to go to their house. So you decide to take the scenic route around the block and go from point A to point B, B to C, and C to D to get to your friend's house. The total distance traveled would be 20 meters plus 10 meters plus 20 meters. So that would be 50 meters if you decided to take the scenic route from A to D. The displacement is distance traveled with direction. Alright, when you are talking about displacement, it is your starting point to your ending point. The shortest distance between those 2 points. So if you started at A and you ended at D, the shortest distance between those 2 points would not be this 50 meters. It would be this straight line from A to D. So your total displacement would be 10 meters south. So if we're talking about you living at A and you went from A to B to C to D, but your displacement would be 10 meters south if we were using a north, south, east, and west direction. So any object that travels in a perfect square or a perfect circle or even zigzags around but ends up back where they started will have a displacement of 0. So you went to your friend's house who lives at D, and then it was time to go home and have dinner. So you went the short way home. You went from D to A. Your distance changes, and so does your displacement. Your distance traveled is now 20 plus 10 plus 20 plus 10. So you've gone a total distance of 60 meters. But your displacement is now 0 because you ended exactly where you started. There is no change in distance and no change in direction. So let's use a coordinate system to figure out the same idea. So this would be a coordinate system. It's a line with units labeled on the line. So it goes from negative to positive. This is something that you have seen before. So where would a reference point of negative 4 be? So if we start, and I'm going to use a random shape to designate this, you start at 0. So that's our starting point. Where would a reference point of negative 4 be? 1, 2, 3, 4. And I'm going to use another shape to designate that point. So I'll use a circle to designate the reference point for number 1. That is where negative 4 would be. So we used a circle to designate that spot. Number 2, if an object had a movement, and we're going to call these units. So if an object had a movement of positive 6 units, where would its end reference point be? So it went from 0 to negative 4, and then it had a movement of positive 6. Where would its end reference point be? So we're going to move this positive 6. 2, 3, 4, 5, 6. And I'm going to designate that with a triangle. So its end reference point would be at positive 2. That's where its end reference point would be. If that object then moves 4 points to the left, would it have a positive or a negative movement? So it started at a positive 2, and we're going to move it 4 points to the left. Would it have a positive or a negative movement? It would have a negative movement. What is the total distance traveled for that object? Total distance traveled will be represented in units. We started at 0 and we went 4 units to the left. Then we went 6 units to the right, and then we went another 4 units to the left. So our total distance traveled would be 14 units. What is the total displacement? And remember, displacement is found by looking at the starting point and the ending point. And our object ended at, from this positive 2, it went 4 places to the left. 1, 2, 3, 4. So the two shapes designating our first and our last points would be the star and the triangle. So it had a total displacement of 2 units. And we will have to always include direction in displacement. So we would say 2 units to the left. And that would give us our total displacement. Sometimes when we are talking about change in direction, we also want to know how long that object took to get there, and that would be change in time. So change in time is represented by this equation. T2 means our ending time, and T1 is the starting time. That is the change in time equation. So let's try that together. If I leave my house on a bike at 3:45 p.m. and reach the ice cream shop down the road at 4:19 p.m., how long did it take me to get there? Now, in some situations, the equation is very useful, and then in others, it may be just as easy to work it out on your own. So I know that from 3:45 to 4:15 is 30 minutes, and then I add an extra 4 on there from 15 to 19. So that gives me a total change in time of 34 minutes. Not 34 hours or 34 seconds, but 34 minutes. If it only took me 34 minutes to get to the ice cream shop on a bicycle, I would probably be very happy and have ice cream all the time. Let's look at change in distance and change in time together on a graph. So what can we learn by looking at these two graphs? First, let's look at them individually. The graph on the left is represented, the object is represented by a red line. So as it moves to the right, that is time in seconds, and as it moves up, that is total displacement. And we're going to represent displacement by feet, because that's an easy measurement for us to visualize. The object on the left the red line tells us that over 36.49 seconds, the object traveled 100 feet. The graph on the right, the blue line, tells us this object also traveled that same 100 feet, but it only took 10.49 seconds. So the blue line object was faster. It took less time for that object to travel the 100 feet, so it was faster. Let's look at them together on the same graph, because quite often scientists will use graphs of displacement versus time to represent that motion. If we wanted to give a complete scientific description on the movement of one of these objects, we would need to be specific, because a complete scientific description leaves no guessing as to how far and how fast and what type of distance an object has moved. So if we're talking about the blue lined object, we would say we're going to say it's a car. So that car moved 100 feet north in 10.49 seconds. So in order to give that complete scientific description, we have named the object, we've said how far it moved, in what direction, and what the speed was. The last coordinate system that I want to talk to you about is a Cartesian coordinate system. And the reason we want to talk about this one is sometimes we need another variable besides besides that straight line coordinate system over a distance, because objects don't just live in a two-plane world. So a Cartesian coordinate system shows the location of specific points on two different planes. So it divides the space into 3 different axes: an x-axis, a y-axis, and a z-axis. And that z is the new one that we're talking about. So that represents that up and down. We've talked about the coordinate systems that deal with the left and right, front and back, but now we're adding that up and down. If you, for example, wanted to tell, if you got your kite stuck in a tree and needed a parent to help you get it out, you would need to tell them, where that kite was located on that Z plane. You can say it was, 15 yards from the house, 15 yards east of the house, and 30 feet up in the air. So that would give an exact point as to where that object is. And you can see on this graph, it is represented by the X, the Y, and the Z, not just that X and Y variable. So that is all of Unit 4, Force and Motion, Lesson 3. Retake the assessment if you've taken it already and have not reached that mastery level. If you take it again after this and you do not master it, give me a call, send me a K-mail, or send me an email, and let's get together in a one-on-one session and look over the questions you got wrong so we can get you to that mastery level.